Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture. In the last lecture, we saw the Hamilton's principle and derived the governing differential equations from there. Now, today we will talk about the solutions. So, as we saw before, for static cases, the solution can be done directly from the variational indicators, I mean the energy expression, or it can also be done starting from the governing differential equation by multiplying some test functions. Now, when we multiply test functions, we saw two approaches. In the first approach, we just multiply it and do not do any integration by parts. In the second approach, we do integration by parts to divide the derivatives as evenly as possible. So, again we look into all the three approaches for this dynamic problem. Now, our equation is, so we have written the static equation which we already derived there. So, we will just add the extra terms that comes here due to the dynamic nature. So, this equation we already knew, we saw it while solving the static problem. Now, because the problem is dynamic, we are going to get one more term here, which is this. Plus this. So, this part comes due to the inertia. Similarly, we can define the error function. If you want to define the error, again this is the error that was there when we were solving the static problem. Now, the problem has changed. So, we have to add more term to the error, and the error is this. Now, what we do is we multiply the phi's to the error and make that integral 0. We have already defined the error, phi has to be assumed as we did before, and after we multiply this phi, the solution comes in the form of a matrix. For the static case, the solution came in this form. Now, for the present case, the solution would come in this form. Now, previously we assumed our phi as, so we had u 0 as a function of x, and our assumption was this is phi u I as a function of x multiplied by q u I. Now, here our u is function of both x and time. So, it is x and t. Now, phi remains a function of x, it cannot be a function of time, but now this unknown q becomes a function of x, and I goes from 1 to m, the number of approximations for u 0, that is m, and w was similarly we can write as a function of x and time as I is equal to 1 to m phi w I x q w I t. So, these q's are now function of x, and q, we as we know, q is just the vector where we have q u 1 up to q u m and q w 1 up to q w m q w n. So, this is now our governing differential, this is now the equation which we have to solve. So, here we have got rid of all the partial derivatives. Now, when the problem was a static problem, from the partial differential equation, after applying the Galerkin technique, we got a set of algebraic equations. K q is equal to f was an algebraic equation, but now the problem has a dynamic nature. So, instead of having an algebraic equation, we are getting a system of ordinary partial differential equations. So, again, for a static problem, from the partial differential equations we get a set of algebraic equations. I mean, when we get rid of the space dependency, we get a set of algebraic equations. For dynamic problems, after getting rid of the space dependency, we get a set of ordinary differential equations. So, it becomes the initial value problem now. Here the generalized stiffness matrix K I j, we already wrote it. Now, accordingly M I j is going to be 0 to L phi I transpose minus M b S b del x S b M b minus, so here it will be S b del x, and here we have M b minus del x I b del x, and this gets multiplied with phi j dx, and this phi I j, they are same. Force we already know, we did it while solving the static problem. So, this completes the first approach. Again, here we did not shift the derivatives using the integration by parts. So, because of this, while we approximate our phi, we have to make sure that these derivatives all exist for phi. Now, in the second approach, what we will do, we will shift these derivatives. So, in that case, the requirement of the differentiation, order of differentiation would be less. Now, in the second approach, when we again use Galerkin method, but we shift the derivatives. Here what we do is we multiply the differential equation, ordinary differential equation, by a test function. So, the first ordinary differential equation which we have, we multiply that with phi u I, which can be seen here. This is the first differential equation. Now, and in the differential equation, in the terms for u 0, we substitute j is equal to 1 to m phi u j q u j, and for w we substitute j is equal to 1 to n phi w j q w j, and in this substituted form we multiply phi u I. So, this is u I, this is phi u I. Okay. Now, we have this term here, we do not have any space derivative. Here we have a spatial derivative, but we do not do anything with that. Here we have a spatial derivative which we shift, which we did before also. Here we have a spatial derivative which we shift. and we also shift these derivatives. So, the first term comes as it is, the second term comes as it is. In the third term, which we already did before for the static case, again we are doing integration by parts. So, this is considered as the first function. So, this multiplied by integral of this, which is this at the limits 0 and L, and then with opposite sign the derivative of this and integral of this, which is this integrated from 0 to L dx. Same thing is done for this term here, same thing is done from this term here, this comes as it is. Now comes our second differential equation. In the second differential equation, again we substitute the same things and we multiply the equation with phi w I. And here we can see that this term has a special derivative which we will be shifting, this does not have any special derivative, and this has a special derivative which we will also be shifting, and here we have special derivative to shift, here also we have special derivative to shift by integration by parts, same thing here. So, that is what we do. This term comes as it is and then we shift the derivatives and we get this term. So, we had we shift the derivatives here. So, this is the first term, this is the second term, and we can see that the derivatives have been equally distributed between phi w I and phi w j, and then we do the same thing for the other term in the among the inertia terms, and we thus do the same things in the other terms as well, and finally finally we get this expression. So, here we have a set of boundary terms and the integral terms, and then after dropping out the boundary terms we get these two equations, and then finally this gives me a set of m plus n equations. So, here this is m equations because phi I goes from 1 to m, and here we have n equations because I goes from 1 to n. And as we have done before, this can be written as a set of ordinary differential equations as this. Multiplied by q dot plus the stiffness matrix multiplied by q, and that is equal to the force vector F. This we already know. While solving the static problem, we got this system, a set of linear simultaneous algebraic equations, and again because it is a dynamic problem we get an inertia term. So, it becomes a set of coupled ordinary differential equations. Here m u u I j. So, this is again m by m, this is m by n, this is n by m, this is n by n. So, this is also m by m, this is m by n, this is n by m, and this is n by n. and this is m plus n by 1, this is also n plus n by 1, this is also m plus n by 1. So, MUJ becomes MB phi UI phi UJ dx, MUW IJ becomes minus of SB phi UI phi WJ comma x dx, and MWU IJ becomes minus of SB phi WI comma x multiplied by phi UJ dx, and MWW IJ is 0 to L, MB phi WI phi WJ plus IB phi WI comma x phi WJ comma x integrated from 0 to L. These matrices K and F we already know. So, if you just write it once more, it is Q U I Q U U I J is equal to 0 to L E A total phi U I comma x phi U J comma x dx, K U V I J is equal to E S total phi U I comma x phi W J comma x x, and K W U I J is equal to E S total phi W I comma x x phi U I comma x dx, and K W W I J is equal to E I total phi I comma x x W I comma x x phi W J comma x x. This is and then dx, and F we wrote as F U. So, this has m component, this has n component. So, F U I is N P phi U I comma x dx plus P x phi U I dx, and F W I is equal to M P phi W I comma x x plus P x P z phi W I dx. So, this completes this equation. We can solve this equation as an initial value problem, and we will get q as a function of time. So, that will tell us at each time step what is my q, and if we get the value of q at each time step, then we can back substitute to the approximation, and that will give us what is the value of u 0 and w at each time step. Now, we will look into the other approach, where we directly put the approximations in the variational indicator and solve it. So, this is our variational indicator. So, we started from the Hamilton's principle, and then we got rid of the time integrals, and we came to this expression, we came to this intermediate expression, which is kind of analogous to our virtual work expression. So, in this expression now we will if we put the approximations directly, then can we get the solutions. Again we have the same approximation for phi u and we have the same approximation for u 0 and w, and we know that epsilon 0 is del u 0 by del x. Now, here it has to be modified now, it is no more a function of only x. So, epsilon 0 x is modified to be epsilon 0 of x and time. So, this takes care of the time part, spatial part, this takes care of the time part. So, we can write function of x, and this is function of time. So, epsilon 0 x can be written as del u 0 by del x, and which can be written as this, and then k x kappa is also a function of x and time. So, this is not this, and then again this is a function of x, and this is function of time. So, we are familiar with this expression, we did it before also. The only difference is that now these q's are function of time. Now, if we look at the previous expression that we wrote here, this expression, it can be written in a compact form here. So, we can see that if we multiply this vector of these double dots with this matrix, and then if we multiply here, we get all the terms related to the inertia here. Similarly, from this term all these multiplications, and from all these multiplications we get whatever we had here, and from this multiplication we get all these terms. Now, if we look at this u 0 double dot, w double dot, and del w double dot by del x, this can be written as this matrix of phi's multiplied by these q's. So, here q's also have to be dotted, because we have put double dot here, and these also have to be dotted. Similarly, if you want to write u 0 w and del w by del x, this will become that same G matrix multiplied by Q. So, when we have u 0 double dot, w double dot, del w double dot by del x, it is G matrix multiplied by Q dot. When we do not have the dots here, it is G multiplied by Q. This we have already done. Now, this we got from the static cases, we already did this, and here we have B multiplied by Q. U 0 W we have already done it, and we got this. Now, what we do is we put these expressions in this expression. We put all these approximations in this expression, and from there we get the solutions. Now, to do that, we can write the first term, which has all the inertias, as 0 to L delta of q t multiplied by g t multiplied by h multiplied by g multiplied by q double dot dx, because we have seen that u0 w del w by del x is equal to g multiplied by q. So, u0 w del w by del x transpose, which is a row vector, that becomes q transpose g transpose, and then if we take a variation here, the variation comes here, and then plus, as we wrote for the static problems, it is delta q t multiplied by b t multiplied by d multiplied by b dx, and then we have 0 to L delta q transpose c transpose px pz dx, and then we have 0 to L delta q transpose bt multiplied by np mp dx, and that is equal to 0. So, again we have delta q transpose everywhere. So, after getting rid of this, we get an equation of this form. We can directly write the equation in the matrix form, and the equation looks like this. mq double dot plus kq is equal to f, where m is integral of 0 to L, integral from 0 to L g transpose h g dx, and then we have the K matrix, that is B transpose dB dx, and then we have the force vector as 0 to L C transpose Px and Pz dx plus 0 to L B transpose Np Mp dx. Now, if we go back, we can see that G matrix is 3 by m plus n. So, G transpose is m plus n by 3. H matrix is 3 by 3 matrix. This we term as H matrix. This matrix, let us term that as H matrix. So, it is a 3 by 3 matrix. So, it is a 3 by 3 matrix, and then G matrix is 3 by m plus n. So, if we multiply this, it becomes a m plus n by m plus n, and this is also m plus n by m plus n, and this is m plus n by 1. So, again we have a system of coupled or ordinary differential equations, solving which we can get our solution. Now, in all the problems we have got the equation in this form, where we have inertia term, we have a stiffness term and the force vector. But in what happens is, in real life there is always a damping associated with this, which we cannot get directly from where we started. So, what is generally done is, artificially damping is added. Very common way of adding the damping is writing the damping matrix as a combination of the mass matrix and the stiffness matrix. Now, these alpha and beta, these factors can be found out when the damping ratios are known, and this is called Rayleigh damping. So, it is artificially added damping, and then this entire combination of the equations are solved and the solution is obtained. So, with this I would like to conclude this lecture here. Later on we will see how these problems are solved, how these ordinary differential equations are solved, and we will see some more cases. Thank you.